Welcome back, everyone. We are now in Chapter 7, Module 7, and we are going to be talking about confidence intervals. A confidence interval is basically our best guess of an interval of a number that we're hoping to capture, what's called a point estimate. Point estimate is a single value used to approximate a population parameter. Now, when we say parameter, for this course, we're talking about three things. We're talking about the mean, the proportion, and the standard deviation. Those are our three. We're going to start with proportion. That's part one here. And we will get to that momentarily. A few more things we need to know. A sample proportion, that's P with a little hat over it, is the best point estimate for the population proportion, regular P. And we'll do a quick example here. 85% of 1,007 adults knows what Twitter is. Based on that result, find the best point estimate of the proportion of all adults who know what Twitter is. So our best point estimate is right here. Here's our P hat. And we would use this as a guide as to what the real proportion of all adults are, because we only surveyed 1,007. So that's based on, that's what P hat is. It's based on a sample. And certainly if we're talking about all Americans, there's obviously a lot more than 1,007 Americans. Next definition, we have a confidence interval. Is a range of values used to estimate the true value of a population parameter. Again, the parameters are going to be one of these three here. For this first section, we're using for the proportion. All right, so we will be given what's called a confidence level. And that is often known as the sea level. So when you hear me say sea level, I'm not talking about the ocean. The sea level is the probability that the confidence interval actually does contain the population parameter, proportion in this case, assuming that the estimation process is repeated a large number of times. So this is often set. Whoever is running the experiment can set their sea level however they want to do it. But let's do some common ones. A common sea level is 90%. Which means our alpha has to be the percent that's missing out of 100%. So that's going to be 10%, and we put 0.1. 95% is a common sea level. That would correspond to an alpha of 0.05. And a 99% would correspond to a 0.01 or a 1%. All right, so we are now to critical values, and we will be using critical values quite a bit as the semester goes. And I should write out critical value. Critical value is the number on the borderline separating sample statistics that are likely to occur from those that are unlikely. And we use the number alpha over 2 is a critical value that is a z-score with a property that separates an area of alpha over 2 in the right tail of a standard normal distribution. And so let's talk about how to find this. So let me draw the first one, the 90%. Oh, a little crooked there. So the 90% in this case, this is always area to the right. It's always the right tail. And this is going to be, now I want to be clear, this is going to be z sub alpha over 2. Alpha in this case is the 0.1. So half of that is, let me do this, alpha over 2 equals z of 0.05. So we know that this is 0.05. And you're going to end up with, I have to use inverse norm because we're given, let me show you again how to do that. So that's going to be here, second distribution, inverse norm. Remember, inverse norm is always area to the left. You'll notice 0.05 is area to the right, which means I have to go 1 minus 0.05. If I don't, then I'll get the negative value. You can just change it. So 1 minus 0.05, giving us, 1 point. .64 looks like. And our z sub, now if I take the 95, here's alpha. Alpha over 2 is going to be half that. If you remember, 0.05 divided by 2 is 0.025. So this is now going to be inverse norm, 1 minus 0.025. .96. The last one. Now, 0.99 corresponds to an alpha of 0.01. Half of 0.01 is 0.005. 0.005 there. Now, you got to have 2 zeros there. It's easy to put 0.05 like there. That's not right. So z sub 0.005. So that's going to be inverse norm again. Now you can see what I'm doing. So let me start again here. C sub alpha over 2 corresponds with a 90% level here. Let's get both, yeah. So here's 90%. There's the 10% alpha. Half of alpha is 0.05. So I did in the calculator. This one, 0.95, half of that is 0.025. I did inverse norm to 1 minus that. And then this one, I'm going to do inverse norm. Inverse norm. Oop. There we are. Inverse norm of 1 minus. Now, that's going to be 1 minus 0.005. There we go. 2.58. And we use these quite a bit, although you can always regenerate them with the calculator, which is what I do usually. All right, page 2. All right. Definition: confidence interval for proportion, population proportion P. And when data from a simple random sample are used to estimate a population, the margin of error is the maximum likely difference between the observed sample proportion and the true value of population proportion P. Again, we're always looking for the actual P. P hat is from a sample that we're going to use to infer something. All right, so here is the formula for the margin of error. So we say E is the error, is z sub alpha over 2, which we just learned how to do, times the square root of P hat times Q hat over N. And once again, Q hat is just 1 minus P hat. And that brings us to our actual confidence interval. So we're going to use our sample proportion, whatever that value is we get from that, So here's our actual confidence interval. So what we're going to have to do is calculate out E and then subtract E from P hat and add E to P hat. And then that'll give us our boundaries of where we think the actual whole population proportion actually is. We've got a few requirements. The sample is simple random sample. There are a fixed number of trials, and trials are independent. And NP and NQ are both bigger than or equal to 5. Let's do our first example. All right, here we go. 1,007 randomly selected US adults showed that 85% of the respondents know what Twitter is. Part A, find the margin of error that corresponds to a 95% confidence level. So let's start here. So our C level is at 95%. If you recall, that means that alpha is 0.05. And alpha over 2 is 0.025. Now, I could use my table, but I'm going to show us again how we can get that. So I'm going to do inverse norm 1 minus 0.025 there's our 1.96. So let's find E. Also, let's write this out. So 0.025, 1.96, it's an estimation. It's 1.96. We also have that P hat is 0.85, which means Q hat is the complement of that. 1 minus 0.85 is 0.15. And then we have N, which is 1,007. All right, here we go. Square root of, I am using this formula here. All right, so we have 0.85 times 0.15 over 1,007. Drum roll, please. Here we go. So I'm going to use that number. I may as well keep all the digits. Times the square root of 0.85 times 0.15 divided by 1,007. I want to warn you, my calculator may work a little bit differently than yours. You'll have to be careful with some of the parentheses in some cases. We should be getting this. 0.0221, we'll say. And I'm going to save this into a memory. Remember, I'm going to store it into memory A. That way I get all those digits and I don't have to write them all out. That was part A. Part B. Find a 95% confidence interval. So now I'm here. So P hat, if you remember, is 0.85 minus 0.0221. This side is 0.85 plus 0.0221. Now I'm going to use the letter A that I stored this off with the memories to do this. So here we go. 0.85 minus A. There it is. 0.8279 and 0.85 plus A. 0.8721. So here's what this means. I'm 95% confident that the true population proportion is between here and here, between 83% and 87%. Now part C says, based on the results, can we safely conclude that more than 75% of adults know what Twitter is? And I'm going to say, yeah, because we think that the true proportion is between 83% and 87%. So can we safely conclude that 75%, more than 75%? The answer is yes. It's because 75% is way lower than this. So it's more likely it's going to be between 83% and 87%. All right, for this next part, I want you to visualize algebraically solving for n. So I could divide by z, square both sides, cross multiply and so on, and we'll end up with this next part. Determining a sample size for the population proportion. All right, here we go. When an estimate p hat is known, then we have a formula, and this formula comes from this other one, this one right here, but again, algebraically solving for n. So it's going to look like this. N equals z sub alpha over 2 squared over e squared p hat q hat. This is if this is known. Because if we have p hat, we also have q hat right away because it's just a complement. Now, when we don't have p hat, when it's missing, and the formula changes slightly. This is squared. And where does that 0.25 come from? Let me show you. So let's say that p hat is 70%. That means p hat times q hat is 0.7 times 0.3. And you can see we get 0.21. Let's get a little closer. Let's say it's 60% and 40%. 0.6 times 0.4, 24%. So let's make it 50-50, 0.5 times 0.5. That is the largest that product is going to be. That's why we have 0.25. We want to give it the best chance and overshoot what n needs to be as needed. All right. I put a quick note here. If n is not going to be a nice, pretty whole number, which it rarely is, you always round up. Because again, we want to know the minimum number of samples that we need to guarantee a certain percent. And we would rather overshoot it than undershoot it. All right. Example 4, how many adults must be surveyed in order to be 95% confident that the sample percentage is an error by no more than 3 percentage points? All right, let's see what we have here. For this one, p hat is known as 0.66. Which means q hat is 0.34. Part B is, what if we don't know? So part A is going to be this formula, part B is going to be this formula. All right, we have that alpha. We have alpha is 0.05, which means alpha over 2 is 0.025, which means z sub 0.025 is the 1.96. I only know that because we just did that for the previous example. Here, 1.96. All right. And also, I still have that stored off as A, I believe. No, I don't. That's a different number. So let's store that anyway. So distribution, inverse norm. There it is, 1.96, store as A. Now you might be wondering what happens to that other number when I store it in the same thing. It erases the previous number and puts this new one in. All right, so we have our alpha over 2, which I stored as A. We have P and Q. E is in error by no more than 3 percentage points, so 0.03. So N is going to be 1.96 squared. And again, I'll use my stored memory there. P hat is 0.66. Q hat is 0.34 over 0.03 squared. Here we go. So A squared times 0.66 times 0.34 divided by 0.03 squared. Here we go. So as you saw, this came out to be about 957.8, which again, we always round up to 958 adults. And part B says, what if we don't know P hat or Q hat? No problem. That just means we're going to use this formula. So we're going to use the 0.25 instead of the 0.66 times 0.34. So N is 1.96 squared times 0.25 over 0.03 squared. And here we go. So A squared times 0.25 equals divided by 0.03 squared. Okay, so that's 1067.07. Now, even though it's closer to 67, we're going to round up. (1,068) adults. All right. Sample 5. Of the 71 subjects in a study about abstaining from smoking for 8 weeks at a 95% confidence interval of, and they actually give us the confidence interval, is constructed. Use this, that statement to find a point estimate P hat and a margin of error E. Okay, so I want us to go back to our definition. Here's our confidence interval. So minus E, P hat plus E. We also know 0.5981 and 0.8104, which means these have to be equal. And these have to be equal. Which brings us to P hat minus E is 0.5981, and P hat plus E is 0.8104. Now, think back to your algebra class. This is what's called a system of linear equations. And we're going to use what's called the elimination method. And I'm going to add these two equations together. P hat plus P hat is 2P hat. You can see negative E plus E goes to 0. They're gone. I'm going to add these up. 0.5981 plus 0.8104. 1.405. And now I'm going to divide by 2. P hat is going to be divided by 2. 0.70425. Now they want both P hat, which I now have. So here's one of my answers. But they also want E. So I'm going to plug in to this equation here. So I'm actually going to plug this. Use my color. I'm going to take this value and I'm going to plug it into there. So 0.70425 plus E equals 0.8104. 8104. Ooh. All right, so now I'm going to subtract. So E is going to be 0.8104 minus, and if you remember that trick I showed you, I'm going to do the previous answer. So second previous answer, meaning 0.7 and all that. There we are. So welcome to confidence intervals.